Okay, hello everyone. I'm Alpin. This is Roman. We're going to be talking about the security surface of the Cosmos SDK, specifically focused on footguns that are particularly easy to trip on if you are not experienced building sort of with this stack. And to Sunny's comment, we do have a fun twist. But before that, we're both protocol engineers on the core Osmosis team. And this talk is intended to be the accumulation of years of scar tissue from the whole Osmosis chain development team that we've sort of just crowdsourced together and put into what was originally a post. And now we're sort of going to be presenting components of it. As a brief overview, we're going to go over the general classes of bugs very quickly, and then we're going to be doing what we'll call a security cage match, where basically Roman and I have prepared questions that the other person has not seen before, and we're going to do a competition where we ask each other, sort of put up a code snippet, and the other person has to figure out what the bug is. However, there are two twists to this cage match. The first is that the loser has to spin a wheel, and we'll show what the wheel is. So the wheel has, mostly not that bad things. There's 10 push-ups, and then for the people who can't see, the other three ones are a clown hat over the course of DEVMOS, an Osmosis fake tattoo, and defending Jacob on Twitter. Those are the stakes. We're gonna be at the end, and we'll spin the wheel even if the person doesn't get it wrong, just to see what would have happened. All right, so hand it to Roman to talk about the classes of. Just to be clear, we're not going to be talking about security issues sort of at the contract level in CosmWasm or around the sort of IBC. Those are massive surfaces as well. We're going to be focused on the Cosmos SDK and the state machine in particular. Go ahead, Roman.
Thank you, Alpin. So let's now go.
Oh, wait, sorry. The second twist is that the audience can interrupt and answer, and if the audience gets a question before the person does, then it counts as a loss.
All right. So now let's go over the high-level categories of these different classes of issues. So the number one that is the most common is centered around non-determinism. So what that actually is that for the same input, all nodes in the network must produce the same output. And if that does not happen, then there is a likelihood of nodes. There is a high likelihood of nodes producing a different state root hash and a chain to fork, and potentially also honest validators to be unfairly slashed. As a result, we as developers must be very careful about the determinism issues. The next class is focused around in-protocol panics. And most of us here are developers, so we are probably familiar with how consensus interacts with the application via the ABCI API. And one of the primitives there is that when executing a block, we also have various hooks. This is what we mean by in-protocol execution. And there is a begin and end block hook. One runs before executing the block against a state machine, and another one after. We left some examples here on the slides, but a perfect example in the context of Osmosis is a module developed by the Skip team, which is Protref. What it does is it backruns user swap transactions to exploit cyclical arbitrage opportunities. Thank you. And in protocol panics, when executed either in begin or end block, can cause a chain to halt. That's why this is another class that we are focused on here. The next area is around unmetered computation. So in the Cosmos SDK, only stateful operations are gas metered, the ones that interact with the state. and CPU is usually not gas bounded. As a result, in the context of any expensive math operation that is not bounded, it can lead to long-lasting execution and might result in an expensive chain hold again. The next class is focused around the key value store layout within the Cosmos SDK, which most chains use a package called IAVL, which is a Merkleized key value store. And this leads to developers having to reason about how to format their keys and how to lay out the data. But that opens up a very risky vector that is actually under users' control in terms of how to propagate some of the key values into the store. And if there is, if not proper care is taken to limit in terms of what users can achieve there, this issue can lead to fund drains. And the last but not the least is the class around fee markets and gas issues. And with the broken fee market or not appropriately charging gas, attackers or malicious users can spam the chain, again leading to a chain hold or blocking valuable user transactions. So now I'm going to pass it back to Alpin to describe the rules of our cage match.
All right, time for a cage match. All right, so we're gonna have 6 questions, 3 each, and so we've already gone over the rules. All right, let's get some excitement. All right. Yeah. Good luck, Roman. I think I prepared some.
I'm excited. I'm excited.
Okay, so I mean, like, we don't have a specific. Maybe we can like set a timer or something, or we can just like have a. Okay, we'll just get right into it. Round 1.
Let's start by spinning up the wheel.
Wait, you want to spin the wheel before or after? Let's do it after. All right. I think yours is first, right?
Yeah.
Okay.
All right. I will start by presenting the problem and letting Alpin take a stab at it. All right. Give it a round of applause to Alpin. Thank you. All right. So here we have a code snippet, which is actually taken from the Osmosis code base. And what we as a decentralized exchange must expose is a price oracle, which is a time-weighted average price. The reason why we need to do so is because a spot price is very easy to manipulate. An attacker can potentially move this spot price to the point where they can exploit the chain. And as a result, we expose this query to the smart contracts so that they have a secure oracle. And here, the function takes the start time in terms of from which point to take the time-weighted average price, the quote genome, base genome, and the pool ID. The low-level implementation is omitted for simplicity. But there is one little detail that is very critical here, and I will.
You talked for too long. I already got it, I think. Oh.
Perfect.
Yeah, I wish we had a buzzer. So just to clarify, this is a query which is normally not supposed to be part of the state machine, but I'm assuming the detail was the smart contract exposed. So it's exposed into Cosmos, which means that it's sort of tied into the state machine. And then I see you try to sneak in a time.now here. So this is a non-determinism bug. Is that correct?
Yeah, perfect, Alpin. And
Okay.
nice work. And do you happen to know what is the right answer to this? Like, how would we?
I mean, yeah, you could just replace time.now with like block time from the context, right? And that'd be good.
Exactly. That's perfect. So. But yeah, whenever we are operating in the state machine, we should be reasoning in terms of the block time rather than the wall clock time. So Alpin got that one perfectly.
Oh, cool. You want to spin the wheel? Yeah?
Let's do...
Wait, do you guys want us to spin the wheel? Yeah. All right. Crowd is spoken.
Let's do it.
You know, people are here for.
All right.
All right.
Okay. 10 push-ups.
All right. You can raise your hand. Yeah. I guess if one of the people already know it, then yeah. But did you have that one? Yeah. Oh, all right. So some of the early ones are not that hard. Yeah. Okay. How are we doing on time? Okay. So this is mine is a little simpler. Basically, we're running in begin block, and there's a starting it off easy contract call that's made in begin block, and yeah, assume there's some setup logic, but that this logic is not related to the contract call at all. So it's assume that sudo is implemented correctly and that all the variables and everything are set up properly, and ignore the return values. All right, Roman, it's all you.
All right, I'm gonna try going at it first. So here I'm not seeing that we are charging any gas on the sudo execution. As a result, the contract could potentially be unbounded and lead to a chain halt in the begin block, which is the in-protocol part of the code base.
Yeah, that's right. So basically, nice job, Roman. That was quick.
Thank you.
Basically, in begin block code is even though the gas is metered, it's not capped as it would be sort of within a block. So you can halt the chain just by literally putting like an infinite loop in the contract, and be very careful putting contract calls that get called in begin block. All right, wheel spin, and then we'll go on to the other. Also, the other ones are going to get a little harder, I think. All right.
All right. This is what would happen if we didn't get one. All right. Next round. So this one is a little bit longer, but let me try to break down the context. So imagine that we would like to batch the user orders for several purposes. Number one, to exploit the coincidence of wants. What that means is if two users swap the opposite tokens over the same pool, instead of executing it against the pool for to avoid price impact, we could directly swap them within each other. But also the way that transactions and messages are executed in the Cosmos SDK today is that they go in sequence. As a result, swaps that go over the same pools, they might get different price impact and different amount out depending on what is their order within that block. As a result, we want to batch the orders that go over the same pools as to ensure a fair order execution. So what we do here is we iterate over the given orders within that block. We try to find a route between token in and out. And then at the very bottom, you can see that we would be creating a batched order graph. But the implementation complexity is omitted for brevity. An important piece of context here is that finding routes is an expensive operation. As a result, we would like to parallelize them. So we iterate over orders, spin up like a concurrent Go routine that then searches for that route. and there is a loop at the bottom that collects the results, appending them into the routed orders. But there is one detail about this that that might result in unintended consequences. So I would like to ask Alpin if you have any intuition in terms of what could be going wrong here.
Yeah. I mean, my guess is it's the concurrent go routine, because the order, I mean, the routes will matter, or they're state dependent. So it depends sort of in which order you process the inputs. So if you do it concurrently and there's non-determinism across validators, then this would lead to an app hash and chain halt, right?
Yeah.
Uh-oh. Was it an intentional second bug, or?
I'm actually curious because it's not. Oh, well.
Okay, so
it sounds like.
Wait, guys. So I have a question.
Sounds like we have to spin a wheel for me now.
Wait, all right, settle on. So I have a question. So it seems there is a second bug in here, but the bug was not intentional. So who should spin the wheel, me or Roman? Both. What? I say Roman spins the wheel because he put in the bug without realizing. All right.
Let's spin the wheel.
Go for yellow.
All right.
All right. So now's a great opportunity to talk about there are consequences to not being careful and writing your code, as Roman is learning. Okay. Yeah.
I don't understand why the first bug is not deterministic.
Oh, because when you have so when you parallelize, so just like when you do concurrency, because the order matters, like the route depends on which pools were filled first.
Oh, find route is stateful.
Yeah, of course, right? Because the pools, it matters sort of like which pools you route through. So like if someone swaps on a pool, the optimal route might be different, right?
There is actually like the core issue here is that the results might come in at different times. I think Alpin's point also stands, but the route results might come in at different times. As a result, when we are collecting them and appending into routed orders, the routes would be in a different order. One of the approaches that we could solve this is by sorting the results, or we could also pre-allocate a certain slice and keep track of the index of each route, and that would allow us to ensure the order.
Wait, did I get it wrong? No, both are important.
Both are right. Yeah.
So I think the statefulness matters as well. Yeah, I didn't see the order coming in though. Yeah. Okay. And in interest of time, we can go to the next one. Okay. Oh. Yeah. So this is. He already did them.
I did them.
Yeah. It's the post bear market, Sonny. Okay. So it's a little long, but. Short version is this is a binary search function. You can assume it's like basically correctly implemented, but doesn't have sort of any sort of error bound. There's an important note that I didn't want to do a multi-slide code thing, which is that this binary search gets called in sort of cross-module hooks. So if you're executing or if you're sending a message. It can get called sort of across modules in module logic, I don't think I'll give any more hints.
Okay,
Audience?
My intuition tells me here that due to this being in the cross-module hooks, there might be slow convergence in this operation, leading to a chain hold due to not finding the result in time.
Wait, this is very close. Does anyone want to counter? No. Okay. I think that's close enough. Basically, because there's no iteration cap and rounding isn't handled explicitly, this could, in theory, run indefinitely. And the reason that this would trigger a chain halt is because we have this amazing property of the Cosmos SDK that gas is basically only charged on stateful operations. So because this is not touching any state reads or writes, it would be completely unmetered. So this would run indefinitely and would halt the chain. So yeah, nice job, Roman. Give a round of applause. Yeah, thank you. Okay, do a quick spin. Oh,
yeah, let's do a quick spin.
What was that? You want to go to the next question? Okay, let's go to the next question. The odds
All
are
right.
Yeah.
So here we are creating a dollar cost average order, and this method is executed from the message server. And the order is then later executed at the end of every epoch, which we control via the begin block hooks. But this is actually a side context. I think what's important here is that we charge the fee to the term spam, save the order to store. But the message place DCA order is actually exposed to smart contracts, which is a useful piece of detail here. So I would like to see if Alpin has any
Okay,
guesses.
so I'm assuming when you say the order is to be executed across epochs in protocol, is this like, so it runs in epoch logic, or?
Yeah, but to add a little bit more context, I would even omit that from your...
Oh, okay. Oh, so this is not like that critical of a bug. So what you're saying is, because you're charging the fee, so what's in charge fee? Is it doing like an explicit balance charge, or is it doing like a gas charge?
It's doing a bank balance transfer.
Okay, okay. So that's the issue then. Basically, you have a contract that's going to be calling this message, and the fee is being charged explicitly as a bank balance as opposed to as gas. So the contract has no way of like floating that up to the user. So you basically just DOS the contract here, right? Yeah. Okay. Cool.
That's perfect. Essentially, whenever a message is exposed to smart contracts, if we charge a fixed fee, it will be subtracted from the contract address. And normally, we would like to propagate the charge to the user. So as a result, in such cases, it is preferable to charge gas rather than a fixed fee.
Okay. Let's work. All right. Oh, question?
Is there
Yeah.
a risk that it could charge the wrong account?
So if you, yeah, it depends on how the contract batches things. Yeah, it could, but assuming that the contract only executes when a user submits a transaction, then like running consume gas would just bubble that up to the user that's calling it. So if the contract is doing some sort of batching, like if it's a vault, for example, and it's like doing stuff, then like it would have to handle the logic and how to spread that across users. But yeah. Yeah. Any other questions? Right. Okay, cool.
All right, let's continue.
Okay, so this is the last one. All right, are we? Yeah, sorry. But it's a particularly tricky one because this question is how most people would patch my first question. So basically, we have a contract call in begin block, and then we set a gas limit on it, and we put this in a separate gas meter, and then we charge it at the end and consume gas. So basically, this is like the standard advice on how to patch a contract call in begin block. And I think it's a very insidious bug here that is very easy to trip up, which is why I included it. So good luck, Roman. Oh, yeah.
You can spam from an account that doesn't have enough gas.
Oh, no, that's not that. Yeah. Yes. I think that's I mean, like, all of it's metered in Cosmos, right? So assuming that like Cosmos gas functions properly, that shouldn't be an issue.
Any other?
Roman, do you have?
I'm not 100% sure, but my intuition tells me is that we do not charge the gas from the original context. Only.
No, we do. It's at the bottom. Wait, Sonny, you can't answer. Oh, okay, because I told him this last night. Yeah, you have. You caught this in my PR. Okay, is it fair to say Roman got it wrong? All right, Dave, do you want to?
When you out of gas in Cosmos, we do a panic stack and line.
Yep.
You don't catch the panic anyway.
Exactly. So even though you cap the pseudo call at the gas limit, when that gas limit is hit, what will happen is it will panic and it will halt the chain, right? Which is so what you need actually is to defer and catch the panic. All right, and then we'll spin the wheel. Roman, do your thing, and then we'll wrap up. All right. So sorry for going over. All right, maybe next time, guys. We still need to do them. All right. Okay. 4, 5, 6, 7, 8, 9, 10. All right. Thanks, guys. Here you go.